Most of us accept that the natural numbers 1, 2, 3, 4 and so on are infinite. You might think that the set of fractions is much bigger than the set of natural numbers, because there are infinitely many fractions between 1 and 2, right? Wrong. Let me show you why. Each tile here represents a fraction. So in this first column here, I've got all the fractions with denominator 1. In the second column, I've got all the fractions with denominator 2. In the third column, all the fractions with denominator 3, and so on. The rows and columns stretch off to infinity, so that I've got a grid with all the fractions in. Now in this bag, I've got the set of natural numbers. So how can I pair up all of the natural numbers with these fractions to prove that the set of fractions is actually the same size as the set of whole numbers? Well, I could start by running along this top row. But because the row goes on for infinity, I'm going to be walking forever and I'll never reach any of the other rows. But there's a cleverer way I can do this pairing. If I start in this corner here and start to make a pattern, looking a little bit like a snake, then I'm going to cover every fraction with a whole number. I've got 4, 5, 6, 7, 8, 9. And I can keep on going, and in this way I'll pair up all the fractions with the whole numbers. Because I can do this, we call the set of fractions countably infinite. Although I'm still going to have to walk forever to cover the whole grid, you can see that no fraction is left uncovered by a whole number if I walk in this snake-like pattern. Well, I hope I've convinced you that the set of fractions is actually the same size as the set of whole numbers. But not all infinities have the same size. I'll leave you as a challenge to prove that you can't pair up all the decimals with the set of natural numbers. If you can do that, you'll have proved that there are uncountably many numbers between 0 and 1.